Hi everyone, thanks for joining me today as I talk about orbital representations. If you are following along on a handout for chemistry, this is handout number 19. Otherwise, let me tell you the point of today. At this point, you should already know some things about electron configurations, whether that has to do with the Aufbau principle or the fact that there's energy levels and sublevels, something like that. What we're going to be doing today is drawing something that looks like this. So it's showing the energy level, the sublevel, and the orbital. Or for here's 2p, the energy level, the sublevel, and that there's 3 orbitals. That's what we're going to be focusing on. The arrows represent electrons in order to understand this idea a little bit better of the electron cloud. So orbital representations, by definition, show the distribution of electrons within the sublevels of the electron cloud. A little bit more detail than what was known as the electron configuration. That was the stuff that looked like this: 1s2, 2s1, or 1s2, 2s2, 2p6, 3s1, that kind of idea. It's the same information. It's just that we're using lines or boxes to represent the orbital. So s's all have one orbital, so one box. S's have one orbital, one box. P's have 1, 2, 3 orbitals, so the 3 boxes. But because of the definition of orbitals, 2 electrons can fit into those orbitals at a time. So that's the up and down arrow. So like 1s2, there's 2 electrons in the 1s. 2s1, there's 1 electron in the 2s, and then it just continues from there. The reason we like this, other than it's a little bit more detail, is because it's visual. If you've done the reading already about exceptional electron configurations, you know that visually this makes it more obvious. Full sublevels are way better than half filled. So see how this is half filled, 1, 2, 3. And then partially filled is not very stable at all. So visually, this shows you it's full versus half filled versus partially filled. So other than just giving you some details about what's going on, it also shows you that visual, which is kind of nice. So in order to do this, there's a few things we need to know. We need to know that we're still talking about the Aufbau principle, which means we're still starting at the lowest spot, 1s, every time, and building up from there. And then what we'll be doing is using lines to represent our orbitals. So we review really quickly that s has 1 orbital, P has 3 orbitals, D has 5, and F has 7. So when we draw those lines, those are going to be representing the orbital of electrons. So that's the first thing you need to know. The next thing you need to know is that there's something called the Pauli exclusion principle. So we know that as the sun, or as the Earth is rotating around the sun, it's also rotating on its axis like this while it goes around the sun. Well, the nucleus does, and the electrons do the same thing. So let's imagine the sun is our nucleus in an atom. The electrons are spinning on their own axis as they spin around the nucleus. But the problem is that because electrons are both negative, if they're spinning the same way, they're going to fling themselves out of the electron cloud, and that changes the chemistry of our atom. So instead, what happens is if they share an orbital, they need to spin in opposite directions. So let's imagine one would be spinning like counterclockwise, the other one spinning clockwise as they go around the nucleus. Then they can stay closer to each other. Their charges don't repel as much, and we're going to show that in orbital representations with up and down arrows. So that's what this is saying. There's 2 electrons in this orbital, so they have to be spinning in opposite directions. The up and down arrow shows that. So that's some of the details that you need to know. One more detail you need to know is this thing called Hund's rule. All right, so my analogy for this is, imagine that you were in soccer. See how mad this kid is? Negative energy. Well, it's because it was a really muddy field. They didn't do well. It was kind of cold outside, so they didn't win the game. So when it was time to get on the bus, all the kids look like this. They're grumpy, they're cold, they're tired, they're mad, they lost. Not a good time. So when they get on the bus, every kid chooses to sit by themselves because they're negative, they're mad, they're upset, they're grumpy. They only sit by themselves if they have to. Electrons are the same way. If you have a sublevel with multiple orbitals, every electron takes its own orbital before it will pair up with another one. This actually in the chemistry world minimizes the energy and gives us the lowest energy situation possible. That's a good thing in the chemistry world or in the natural world. And it's maybe a good thing with that team on the bus because then maybe no fights will break out. They won't repel away from each other because they're spread out as much as they can. Hund's rule is the same thing in the chemistry world. So if you have a sublevel with multiple orbitals, they will take their own orbital, the electrons, if they can. It makes the least amount of energy, spreads out that negative charge as much as possible. That's kind of the idea there. So Aufbau principles start at the bottom. Pauli exclusion principle means up-down arrows because they're sharing an orbital, so opposite spins. Hund's rule says if they have to share an orbital, if they have multiple options in a sublevel, they take their own orbital if they can. So let's go ahead and try this out. Oh, first though, I want to talk a little bit more about why the periodic table is shaped the way it is, because it fits into what we're going to be doing today. So maybe you've wondered, why isn't it just like even rows and columns? Like, why is there a big dent in the periodic table? Well, it's because the shape of the periodic table matches our sublevels. So there are 2 electrons that can fit in the S sublevel. So there's 2 columns on the periodic table that match that. There are 6 electrons that can fit in the P sublevel, so there are 6 columns on the periodic table to match those elements. And then there's 10 in D and 14 in F, because that's how many electrons fit. So for example, the reason this isn't moved up is because there isn't a D sublevel in the first energy level. There's not a D block until we fill up the 4s. That's the Aufbau principle. So that's why this is scooted down here. And really, these 2 rows should be right in between here, because there's not a 4F until you fill up the 5D1. And then that's kind of a way to check our work. I'll show you what I mean when we do our first couple examples. So speaking of, let's do a couple examples. So we need our Aufbau diagram. This is going to serve as kind of our reminder of what's going on. And then we're going to need our periodic table. Because if we're going to write the electron configurations, we need to know how many electrons there are. But this is orbital representation, which also shows electron location. So oxygen. Here's oxygen. It's element number 8, which means that it has 8 electrons. So we're going to start with our oxygen, which has 8 electrons. And then we're going to use the Aufbau principle idea, knowing that S has 1 orbital, P has 3, D has 5, and F has 7. And then use this to say we start with 1s. So I'm going to start with 1s. I'm going to give it 1 orbital. I'm going to use a line just because it's easier to draw than boxes. Every orbital can hold 2 electrons, but Pauli exclusion principle says they have to be going up, down to share an orbital. I've got 8 electrons total. This is only 2, so I keep going. After 1s comes 2s. So here's my 2s. Here's my 1 line. Up and down arrow to represent the fact that they're sharing an orbital. They have to be opposite spins. This is only 1, 2, 3, 4 electrons. I have 8 total, so I keep going. So after 2s, I look at my Aufbau diagram. I go to 2p. So 2p, P now has 3 orbitals. So I have 3 orbitals that I need to draw, but I only have 4 electrons left. Hund's rule says spread them out. So here's 1 electron, another electron. My 3rd electron in this sublevel spreads out, but this is only 1, 2, 3, 4, 5, 6, 7. So my last electron will have to pair up with this one, but these 2 don't. That's Hund's rule. So Aufbau principle says start at the bottom, 1s, then 2s, then 2p, only if you have to. Pauli exclusion principle says opposite spins when they share an orbital, and then Hund's rule says spread them out in the sublevel if you can. That's it. That is your example of orbital representations. Let's do another one. Let's do calcium. So we find calcium on here. Calcium is number 20, element number 20, which means it has 20 electrons. So let's try this out. So calcium, 20 electrons. All right, I'm going to do the same thing that I did before. I'm going to start at my 1s because that's always where we start for our Aufbau diagram. So I'm having 1s, which is 1 orbital. Up and down arrows because they have to share. Then I go to 2s, 1 orbital, up and down arrows because they have to share. After 2s comes 2p. 2p, so I've got 3 orbitals now. This time I've got 20 electrons, so this time it will fill, but technically Hund's rule says it fills this one, then this one, then this one, and it only doubles up because it has to. After 2p, I go on to 3s. 1 orbital, so because of s, so up, down arrows, counting, I've got 2, 4, 6, 8, 10, 12, which means I need to keep going. So after my 3s, I go to 3p. I'm at the 3p sublevel, which means I need 1, 2, 3 orbitals. So I've got 3 orbitals that need to fill. I've got 20 electrons total, 2, 4, 6, 8, 10, 12. This will fill, but technically Hund's rule says it goes 1 at a time, and it only doubles up when it has to. This is now 18 electrons, so I double check my Aufbau diagram. After 3p comes 4s. I'm back to the s or sublevel, so only 1 orbital. This will fill up because then now that's 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's a way to check your work. They're all up and down arrows. Visually, it looks like all my sublevels are filled, so that's my most stable option. But think of it this way. The nucleus would be way over here. If it's trying to track all these electrons, that shows us why this 4s with 2 little electrons in it is so easy to be taken away by someone else. Well, if I take these away, that's going to give me a positive 2 charge. That's why calcium has a positive 2 charge. We know that from counting backwards, but the idea is that if it counts backwards, it's like the noble gases, which would be a full S and P. So that's why, all of those things going together. The other thing we can do is we can use this to double check our work. So calcium would be right here. So right after my, in my fourth row, the second one over, well, this is the S block, and 1, 2 over, S2, it's another way to check our work, to use this information to check that. All right? Let's do one more. Let's do yttrium. Here is yttrium. It's element number 39. Look at where it's located. It's in the D block. It's in this middle section. It's the first column, so it would be like D1, telling us that it is going to, so it'll be right here. So D1 is the last piece of my electron configuration, or the last piece of my orbital representation. Let's go ahead and check this one out just so we get a whole bunch more practice doing these. So yttrium, we said, had 39 electrons. We're still going to use our off-bow principle, so we're going to start at 1s. So s's have 1 orbital, so I draw one line, up and down arrow, to represent that they're sharing. After 1s, we can use this for now, is 2s. So 2s, one line for 1 orbital, up and down arrow. After that, the off-bow diagram says 2p. 3 lines, 1, 2, 3, for 3 orbitals. This will fill because remember I got 39 electrons and this is only 10 so far. After 2p comes 3s. So here's my s, 1 orbital, up and down arrow to show that they're sharing. That's the Pauli exclusion principle. 3p comes next. I'm back to p, so 3 orbitals. That's the definition of the p sublevel. It will fill, but technically Hund's rule says it's 1, 1, 1, only doubles up because it has to. What am I at here? 2, 4, 6, 8, 10, 12, 14, 16, 18. Not quite halfway. Wait, let's keep going. After 4p comes, or 3p comes 4s, 1 orbital, up and down arrow. Let's keep going. After 4s, I go back to the bottom here, 3d. Oh, that's going to help out it a lot because remember D has 5 orbitals. 1, 2, 3, 4, 5. Will it fill? Yeah, because I'm only at 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I got to get to 39, so this will all fill. But again, technically Hund's rule says it fills one at a time to spread out the energy, but because it is a full sublevel, all of the electrons pair up. All right, let's keep going. After 3d comes 4p. Normally we would keep going in a big long line, but I'm running out of room, so I'm going to put it underneath it. So 4p has 3 orbitals because that's the definition of p. 1, 1, 1, Hund's rule says, but they double up because they have to. Because this was 30, now I'm at 36. Oh, I got to keep going because I got to get to 39. After 4p comes 5s, so I'm back to my s sublevel, so that's only 1 orbital. Up and down arrow to represent that they're sharing. I'm at 38. Oh, I got one more to do. After 5s comes 4d. There's that d we were talking about that we checked from here that we thought we were going to get to the d block. Well, here's how. So here's my 4d, but again, d's have 5 orbitals. 1, 2, 3, 4, 5. You draw all 5, even though the fact that we only have 1 electron left shows us that yttrium is really unstable right now. Look at all of these empty orbitals. That's not a good option for a stable electron cloud. So what's going to happen is yttrium's going to try to get rid of this at some point. Someone's going to come and try to take it. But look, it's so far away from the nucleus, it has to go through all of these electrons to try to attract it. It's going to be really easy for someone to take it away, which would make yttrium positive, and then all the levels below it would be stable. But then this one is now going to be your tiny little thing hanging out there at the end of the electron cloud. Someone's going to take that too. So all 3 of these are going to end up being taken away, and then the 4p and the 4s will be filled. That's going to make yttrium more stable. But then it's going to have to find a compound because it's going to have a positive charge. So again, trying to make some connections between this visual, this very technical information of orbital representations, and other stuff we've talked about. So again, this ends in D1, which makes sense because look at where it is. It's in the D block, the first column, so D1 makes sense. Just like calcium was in the S block, 1, 2 column, so then it made sense that calcium ended in S2. And then our oxygen one, we didn't check this, so let's check it quick now. This ends in P, 1, 2, 3, 4. Let's see if that makes sense. So oxygen is right here. This is the P block. 1, 2, 3, 4th column over. Yep, then that's going to make sense. All right, so that is your information on how to draw orbital representations. If you are following along for chemistry, the back side of this note sheet has your assignment. Finish that and then turn that in, and of course come in if you have any questions. Thanks for listening.